Imagine yourself on a chilly winter's morning, nestled in your favorite cafe, the aroma of freshly brewed coffee enveloping you like a cozy embrace. As you take that first sip of your beloved brew, you feel the warmth permeate your being, a sensation akin to the flow of energy coursing through a system. What is that energy? What is that heat? In today's video, I welcome you to a journey that marries the warmth of your favorite cup of coffee with the captivating concepts of entropy, enthalpy, exergy, energy, and some other concepts of thermodynamics. My name is Shaunak, and you're watching this video on my channel Physics for Students. Welcome to this fresh new video on the fundamental concepts of thermodynamics. First, we start with a very basic thing, that is, I would say a relationship, or you might call it as a difference between what is a heat and what is a temperature. Well, first of all, before I go ahead into the intricate details, when you're learning temperature, three things, or rather I would say three concepts basically comes into the play. The first one is something which is called a thermodynamic temperature. Now, this is the most fundamental concept. It is based on the laws of thermodynamics and relates directly to the average kinetic energy of the particles in a substance. Here, the absolute zero or 0 Kelvin on this scale represents the point where all molecular motion ceases. So, the first concept which you might encounter is what is called a thermodynamic temperature. The next one is called the SI temperature. So this refers to the practical temperature scale defined by the International Temperature Scale of 1990, abbreviated as ITS 1990, and it uses specific carefully chosen reference points like the triple point of water and defined relationships between them to achieve incredibly precise and reproducible temperature measurements. It is an extremely accurate approximation of the true thermodynamic temperature. And third, what you see is that temperature as measured in physics. So in physics, when we talk about temperature, we typically mean to say, or rather I would say it refers to the measurement of a specific temperature scale, most commonly the Kelvin scale, the SI temperature, or Celsius scale, and so on. So we use thermometers calibrated against that rule which I told you, the ITS 90 or the International Temperature Scale of 1990, to measure this temperature. Now, having said this, as you understand, these are the three concepts, I mean to say, when you're reading the books, etc., of temperature which comes within. So when we talk in general of temperature, what do we mean is the degree or intensity of the heat present. So we say that the body temperature, or I feel a little bit, I've got a temperature. So it is the degree or the intensity of the heat present as shown by the thermometer. Also, it can be defined as the measure of hotness or coldness of a body, which is measured in Celsius, Kelvin, or Fahrenheit. So here the scale doesn't matter. What it says is the degree of intensity and the measure of hotness or coldness. So heat, on the other hand, is some kind of a form of energy that flows from an object at a higher temperature to an object of a lower temperature. So it represents, I would say, the transfer of thermal energy between systems due to a temperature difference. So temperature is basically the intensity, the heat, the coldness, and heat is basically a form of thermal energy that actually flows. So here you can see in this picture, from a warmer object to a cooler object and so on. So when you're reading the concept of it, it is a kind of a flow. It's a kind of a, things that flow, if you want to imagine. So heat actually flows from regions of higher temperature to regions of low temperature until and unless we reach what is called a thermal equilibrium. Now you see, when I'm talking of things which are flowing, etc., that is why the concept of flux actually comes in. So when you're reading flux, as I have explained earlier in my videos in Maxwell's equation, it's a kind of a flow. So imagine a rush, a gush of wind flowing, or when you open the window, a light, the sun rays coming in. So that is why it is called a flow. So the concept of flux comes in. So thermal energy is transferred from one object to another, obviously due to the temperature difference, a difference in temperature. So what we can summarize from here is that heat and temperature obviously are not the same. Temperature remains constant when we are changing a phase. Example, activities like melting, boiling, etc. While heat is either absorbed or released. Now this is a kind of a basic understanding of heat and temperature. But here comes a tabular system where the difference would be much more clearer. So heat is a form of energy transferred due to temperature difference, and temperature actually measures the average kinetic energy of particles. It is measured in joules. Heat temperature is measured in Kelvin, Celsius, Fahrenheit. Heat actually is the capacity which depends on the substance specific heat capacity. I hope you know what is specific heat. And temperature does not depend on specific heat capacity. Heat is denoted by T and temperature is denoted by Q. Heat is not directly measured but calculated based on the temperature change of other scale factors, and temperature scale provides a way to quantify how much hot, how much cold and so on it is. So this actually gives you a basic foundation of what is heat and temperature, difference you can call, or the relationship something, and it gives you a better way to visualize when you're visualizing what is heat. We come to the next part, which is very important in thermodynamics, which is called internal energy and enthalpy. And in order to go forward with making you understand what is an internal energy, I would first use this kind of an animation. So let us imagine this is a box. It contains, you can imagine it's a perfect gas or something. All the atoms and molecules and all the subatomic particles are bouncing and on the walls each other. So first thing is that a thermodynamic system. So let us consider this to be a thermodynamic system which contains some quantity of matter and has within itself a definite quantity of energy. So energy here is conserved. So this energy, remember, it includes not only the translation of kinetic energy, where you can see the blue and the red dots which are bouncing each other, but also other molecular energy which includes rotational, which might include vibrating or bouncing energies, anything. So the kinetic and potential energy of the nuclei of electrons within the individual molecules, remember, it also contributes to the energy of the system, and together we call this one. The total of all the possible kinds of energy of a system is called its internal energy. So this energy is not only the translation of kinetic energy, this energy includes other energies which I told you, and the kinetic and potential energy of the nuclei of electrons, which are the individual molecules or the subatomic particles, also contributes to the internal energy. So taken all those summation together, we call it as an internal energy. Internal energy, technically we denote it by U, which is the total energy within a system due to the molecular motion and interaction of particles. Here is a nice animation, so you can think this to be a thermodynamical system where the total energy is, and these are the molecules which are vibrating. So this is an animation. So the total microscopic kinetic and potential energy of the particles within a system. So it's a system which contains the kinetic and potential energy, and these includes, as I told you, all the types of vibrations of atoms, molecules and whatsoever. So in order to imagine things better, you can think this to be a billiard ball. So it contains all the internal motion of configuration within a system, like a total kinetic and potential energy, the balls on a pool table. Now what happens when you hit the billiard ball, that is a different issue, but you can imagine this to be a collection, all those internal energy within that system. Now as we are studying physics, nothing is clear until we go ahead and describe a mathematical formulation. So here it is delta U equals to sigma I EI, where I would say delta U is basically the initial internal energy which is before that the thermodynamical process starts, minus the final internal energy after the end of the thermodynamic process. Now I am not defining what is a thermodynamic process. Let us imagine it can be anything. So delta U would be that change from the initial before the thermodynamical process starts minus the final, which is after the process ends. And this EI are the various energies transferred to the systems in these steps. Whatever, it can be different types of energies which are transferred. So we can also write this as delta U equals to Q minus W, where Q would be the total amount of heat received from the surroundings and W will be the total work that is done. and we can say that it is also the initial minus the final. So U2 minus U1, which will be equal to Q minus W. That means this Q minus W, which is delta U, which is the initial minus final minus the initial. I have written it again as U2 being the final and U1 being the initial. So that gives you a kind of a brief idea about if we can, although there are many other equations, I just wanted to make it that internal energy that can be. Now we come to the very important concept, what is called enthalpy, which is derived from this Greek word enthalpos, which means putting heat into. And this term was actually coined by this Dutch physicist Heike Kamerlingh-Onnes. I'm so sorry if I'm not pronouncing the Dutch name correctly. So he was a Nobel laureate Dutch physicist and coined the term enthalpy. So we can say H, or we can say H equals to E plus PV, or sometimes in certain books it is also U plus PV, internal energy plus pressure times volume. So we can say enthalpy, I will come to the part, is the sum of thermodynamical systems' internal energy. Obviously the internal energy is something which we have just defined and visualized, and the product of its pressure and volume. So we take the internal energy, which can be denoted either by E or U, plus pressure times volume. Here H is the enthalpy, which is measured in joules. E is the internal energy, which is also measured in joules. P is the pressure, which is defined in terms of Pascal, and V is the volume, which is obviously measured in cubic meters. So in order to give you a better, I would say, visualization of what is an enthalpy, let us think this one. These are molecules which are vibrating. So internal energy considers only the microscopic properties within a system, and enthalpy takes into account both microscopic properties, that means the internal part, as well as the pressure and volume relationship. Now you might be thinking that between this energy, what we call in general energy, and what we call enthalpy, what could be the relation? Is there at all a relation? Definitely there is a relation, and I would like to show you in the next part of the video. So this is again a kind of an animation which you can think, again, molecules or things which are vibrating around. So now you see that if you imagine this one, this on the left hand side diagram, as a closed container with some gas inside, the gas particles have a certain internal energy, obviously due to their motion, which is the kinetic energy, and interactions, potential energy, and you know this is sum total is the system's internal energy. Now suppose I heat this container. So if we heat the container at constant pressure, like for example a hot plate or something, the gas expands slightly, that means increases the volume V, and the internal energy U of the gas increases because the particles move faster, higher kinetic energy obviously, because it will move faster. However, the expansion also does work on the surroundings of the container, that means around the container, pushing it outwards a little bit. So this work done is accounted by the P times V term, which is the enthalpy equation. So therefore the enthalpy that is being taken by H of the gas will also increase because its internal energy is increased, and it did work on the surroundings due to the pressure volume change in this example, since the pressure is constant. So that is how it would be. So therefore the enthalpy of the gas will also increase because its internal energy is increased. So in essence we can tell that internal energy considers the microscopic world within the system, while enthalpy considers both the microscopic world and the system's interaction with the surroundings through the pressure and the volume changes. Now can we define it in mathematical terms? Yes, it is very simple. Delta H equals to delta U plus P times delta V, where delta H is basically the change in enthalpy. We are more actually concerned in the change in enthalpy. I will show you that enthalpy measurement in that way. The total enthalpy is not that important in thermodynamics. This is the change in internal energy, which I told you U2 minus U1, and P is the pressure, and delta V is the change in volume. So we can tell that the total enthalpy system, as I was telling you, cannot be measured directly because you know, the internal energy contains components which are very unknown to us, and these are not actually accessible. So we really are not interested to calculate the total, rather the change in enthalpy. So in practice, a change in enthalpy is the preferred expression for measurements at constant pressure because it simplifies, you know, the description of energy transfer. Okay. We come to now to understand, I won't say again a difference, relationship or whatever, between enthalpy and internal energy. And first the parameter would be the definition. which tells that internal energy is the total energy of a system including kinetic and potential, and enthalpy is the total heat content of a system at a constant pressure including the internal energy and the pressure volume work. So this tabular idea would give you kind of a, I would say, pictorial understanding. Symbol here is U, that is H. Unit is joules and joules. Formula depends on the specific system and the process involved. And here it is simple, H equals to U plus P times V. The components includes kinetic energy and potential energy of particles. Here it includes internal energy and the pressure volume work. Now, in order to make things a little bit clearer, let me give you an analogy where the internal energy is the total energy of including kinetic and potential. And here you can think of energy of balls on the table, that the billiard ball, and potential energy is due to the table configuration. Change in value, obviously delta U will be the final minus the initial, and delta H would be H2 minus F1. Application, yes, internal energy is very widely used in various areas of thermodynamics and physics. This is enthalpy is particularly used in chemistry in constant pressure. Example again would be heating a gas increases its internal energy, and heat absorbed or released in chemical reaction corresponds to what we call is the changes in enthalpy, and we are much more interested to find out or calculate the changes in enthalpy rather than the total enthalpy, because there are certain internal unknown components of internal energy. We come to a very important part next, is that what is called entropy and exergy. Now, I hope you are all aware about entropy, and this was actually coined by this gentleman, Rudolf Clausius, German physicist in 1865. And entropy, you can say it is considered as a scientific concept which is mostly associated with is called disorder, randomness or uncertainty. However, entropy can be extended further to black hole and event horizon. We are not interested right at this moment. So here you can see low entropy, the molecules are arranged, and high entropy, they are distributed. It is measured in joules or kelvins. From a thermodynamic point of view, I would say of entropy, we do not consider the microscopic detail of a system. That is important. And entropy is used to describe the behavior of a system in terms of thermodynamic properties. What are the properties? Pressure, temperature, entropy, heat capacity, etc. And the thermodynamics description took into consideration the state of the equilibrium of the system. This can be elaborated and elucidated to a lot of equations, explanations, which I am not doing because entropy is something which you are quite well aware. I would go to the next part, which is exergy. And this term was coined by Zoran Narant, who was a Yugoslavian mechanical engineer, scientist and a professor. So exergy, means that the maximum amount of usable work. I will give you further examples that can be potentially extracted from a system, thermodynamical system, and it represents the high quality usable portion of the system's energy. Also, it is not just about the total energy that a system possesses, which we just saw, but we are more interested in the maximum amount of usable work you can potentially extract from it. So, unit of measurement is obviously joules, and here you see from the low entropy, as soon as a system goes to higher entropy, as entropy increases, the system obviously becomes more disordered, and the I would say exergy would go down. Why? Because it becomes very difficult for a high entropy system to extract the usable work. Obviously that is true because we won't be able to extract how much is required because the entropy is quite high. Let me give you a simple example. Think of your mobile battery which is a full battery, and exergy would be something of this battery would be its potential to perform all type of tasks. It can be taking photos, making calls, watching this video or whatsoever. So that is a kind of an analogy of exergy. You can also think of this cup of coffee with those beautiful cookies which are my favorite. Now obviously this cup of coffee has got a thermal energy, but the question is that can we use this thermal energy in order to ignite the engine of your car? Definitely not. So it contains thermal energy, but we cannot use that to heat directly to the power of your car. So that means that the hot coffee compared to the cooler environment creates a potential for work. But exergy quantifies this potential, which is for the work, and the usable portion of system's energy considering the surrounding conditions. So that is what, how much, so that is why you see exergy is mostly used in engineering purpose, etc. And Zoran Nat was indeed, engineer, so he used this term. So what are the key points of exergy? Point number one is that exergy represents the, I would say, the usable work potential of a system's energy, and it also depends on the system state. That means the surrounding conditions. Obviously, as per the second law of thermodynamics, it would depend. And exergy analysis is definitely a very, very valuable tool for optimizing use of and minimizing losses. Obviously, we get a system, how do we minimize the loss and use the heat in order to make things work? It's super important. And while there is no single equation of exergy, I have not mentioned, it can be related to what we called enthalpy, entropy, environmental temperature, etc. Also, you will see that by understanding exergy, engineers design more efficient systems, minimizing energy state and promote sustainable resource utilization, which is very important for practical applications. And it is a crucial concept for harnessing the true potential, I would say, energy sources and creating a more sustainable future. So that would be the usage of, I would say, the relation and important points of exergy. Now, if you come to the applications of exergy, as it is very much applicable, the first one, which is for power plant. Yes, it helps to optimize efficiency by identifying and minimizing energy losses in different stages of power generation. Second one would be the refrigeration system, because understanding exergy help improve efficiency by focusing on extracting the most important work from the cooling process which is done. And resource utilization, it aids in evaluating different energy sources based on their valuable work potential, promoting a sustainable future. Now we come to the final part where we try to do a kind of a relationship between energy, enthalpy, exergy and entropy. So we start with the basic part, which is the energy, and it refers to the total heat capacity of a system to do work. And energy can exist in various forms, obviously thermal, kinetic, potential and chemical. Enthalpy, which is denoted by the word H, it represents what we call a total heat content of a system at a constant pressure. So it considers what? Both the internal energy of the system, that means the microscopic properties, and the energy associated with its volume and pressure, which is the macroscopic properties. And the relationship is that the enthalpy is a specific form of energy, focusing on the heat content at constant pressure, and it can be related to the total energy of a system through this equation. So this is actually what is called the relationship between energy and enthalpy. So we come to the next part. What is exergy, denoted by B, and it represents the maximum amount of usable work you can theoretically, remember it is theoretically, you can extract from a system under specific conditions. Now, unlike total energy or enthalpy, exergy considers the limitations which are imposed by the environment, like for example temperature, it could be the second law of thermodynamics, etc. So the relationship is that enthalpy actually tells you the total heat content, but not all that heat is usable at work. That is very important. So only that portion which is, the total part, enthalpy. And what does exergy tells? Exergy depends on enthalpy, but also the factors of the entropy, that is the disorder of the system, and the surroundings. So enthalpy will tell you the total heat content, exergy depending on the enthalpy and also factors in the entropy of the system, which is most importantly making things work. So entropy, and what is entropy, as we have already noted, is a measure of disorder, and it describes the randomness of disorder. So as entropy increases, a system becomes less organized and we cannot make them use. So this is one, a higher entropy. And this increase in disorder is linked to what is called exergy, so it becomes very difficult for us to work. Now, in order to explain all these things, I would take a freshly brewed coffee. So I have this is a kind of a nice coffee with some cookies. So there sits upon a quaint saucer a vessel of warmth and comfort, a cup of steaming coffee, its aroma a symphony of roasted beans and memories, dances delicately through the air, enchanting all of you who draw near to this coffee. I'm to say I want to imagine that beautifully brewed coffee. And taking this coffee cup example, I would like to say you that energy is basically the total energy, total thermal energy of the coffee. The second, enthalpy, is the total heat content of the coffee, considering both its internal temperature and the heat it could release at constant pressure. Exergy is the maximum amount of work that you could make theoretically using the temperature difference between the coffee and the room, etc. And the next one is the entropy. As the coffee cools down, entropy increases. Its ability to work, exergy, is something which decreases. With that, I would like to conclude today's video because I'm really feeling that I should go ahead and have a cup of coffee. Thank you very much for watching this video. If you have liked, please do subscribe to my channel Physics for Students and hit on the bell icon to get all the notification from Physics for Students. This is my email ID and this is my other channel where I put up only videos related to general theory of relativity. Please don't forget to subscribe to the other channel, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Thank you very much for watching this video, and Physics for Students will be soon back. No, not only with coffee, but something very exciting coming up in the next few videos. Thank you very much.